Hello, everyone. Welcome to today's PyHealth slide. This is the 7th slide we have. If you are interested, you should check out previous live sessions. And today we're going to talk about how to build custom model, how to incorporate your custom models into the PyHealth pipeline. My name is Jen Ling, and I'm part of the PyHealth development team, whose members are listed here. We have Chaoqi, Zhenbang, Patrick, myself, and Professor Jim Sun. And also a bunch of collaborators listed below. So a quick overview of something you might have heard of from previous sessions. What is PyHealth? First of all, well, PyHealth is a very comprehensive Python library built on PyTorch that can help domain scientists or machine learning scientists to quickly try or apply machine learning models to healthcare applications. There's several basic modules we have: the EHR database module, the prediction task module, the healthcare core machine learning module, and also the EHR code mapping module. And today we're gonna focus on part of the core machine learning module, which is, like I mentioned, how to use custom model in the PyHealth pipeline. And here I'm showing again a recap of them on a very high level, the machine learning pipeline that you typically have using PyHealth. You need to process the data set first. By the way, all these are part of the modules we have. PyHealth will help you process the data set first. You also define the task, the prediction task you might be interested in. And then you need to initialize your module, and then you have training and inference. Today we're gonna focus mostly on how to essentially define the module. The model. First of all, I want to again do a quick recap of the data input to the models, because essentially we are swapping a component in the pipeline. So we need to know what's the input to this thing that we're going to build and what's the output that we should return. So in PyHealth, we process the patient data into structured data formats like the one listed above. I'm showing one example there. Here we have a patient with patient ID 153, a bunch of other features, including gender, age, conditions, procedures, medications, etc. Now, that's one single data instance, and typically you will have a data loader that can produce batch of data, and this data batch is what we will be feeding into our model. However, the issue is, if you suppose you have a PyTorch model defined like on the right, it typically will take some PyTorch tensors, right, and some other arguments, but it doesn't just take this data batch and produce something. So we need to find a way to wrap this PyTorch model using some of the utils and functions we have in PyHealth, so that we can easily swap this model into our existing pipelines. So that's what we're going to talk about today. Throughout today's tutorial, I'll be using a model that's kind of classic and it's been around for a few years at this point, called Deepr. And if you're interested, you could go to PyHealth website under advanced tutorials. The third tutorial has all the code that we'll be using today. You can run the notebook along with this tutorial. So my assumption is that we will have a PyTorch model. As usual, it's a torch.nn module. You're taking some PyTorch tensors, maybe some additional arguments like a mask in this case. So very quickly, a Deepr layer is essentially doing a 1D convolution on all the code, and then takes a specialized max pooling at the very end of the computation. So that's essentially what's in this PyTorch version of the Deepr. So if you want to use this module, well, you will pass the PyTorch tensor, right? So here I'm passing in the tensor of straight 2 by 128 by 5. Here the 5 is the hidden size. So after the summary, the model, well, the model would need to take in, sorry, the feature size, which is part of the parameter. After you pass that input through this PyTorch version of Deepr, you get the output tensor. Right? Again, this is an output of a batch size of 2, but then this time the embedding dimension is 3. The second assumption I'm going to make is, well, suppose you have this Deepr, you want to build a PyHealth wrapper around it. You probably want to use such model for more than just one task. For example, you might be interested in using it in a binary classification task, multi-class classification task, or a multi-label classification or regression task. So, well, here I'm using this Deepr mostly as an embedding, most like an encoder to the input. And another thing before I go into the actual example is that we're only going to process one specific type of input in this tutorial, which is list of code. So this is a very typical type of input in ESGR data. You can think of the first layer of the list as the visits, and then the second layer as the code within each visit. Okay, so I'm putting the data and how we are going to initialize our model on the left. So the first thing we need to do is define an init function. And don't worry, we're only going to need to define 2 functions. One is the init function, the other is the forward function. So for the init function, the first thing we need to do is inherit create an instance of base model, which is a existing template in PyHealth library. And because this base model class will require some attributes, we're initializing them in this first step, which I'm showing you here. In the future, we are planning to move this into init function of this parent class of base model. So you might not need to do this in future versions of PyHealth, but for now, we still need to do this, mostly just a copy paste for every model. The second part that we need to do in the init function is that for each of the features, we're gonna need a feature transform layer, and this is how we add such transform layers. So remember, the feature keys here correspond to the feature keys here. So in this particular case, the feature we will be feeding into this model is this abstract term list code, and the example is given here. But in many cases, you might have more than one feature keys, or maybe you have a bunch of lists of codes like drugs, conditions, etc. So for each of those, we will be needing one feature transform layer. So that's what's happening here. As you can see, initializing such layers are very easy. You just need to pass in the input information, which contains things like, how many levels of nesting you have in this kind of feature, or whether it's a string or the integer, etc. And then this function, add feature transform layer, would create some embedding layers or like tokenizers and add them to these dictionaries or module dict, depending on the nature of those layers. The next part of this init function is initializing those PyTorch version of your model. You could skip this step by directly defining whatever models in this init function instead of creating a different class. But I'm like doing this just for modularity. So again, we're gonna create one PyTorch Deepr encoder for each of the feature keys, just like before. And finally, we need an output layer. So the interesting thing here is that you can simply use this get output size function to compute your output size. And this is going to be inferred based on your data set. For example, if it's a binary classification task, this should be 1, I think. And then multi-class, you will infer the number of classes, and then generate output this output size. So you can just create the last layer using this output set. So after we have the init function, all we need to do is the forward operation. Don't worry if it looks like a long function on the first glance, because I'm going to walk over every step here. So first of all, as you can see, we're iterating through every feature keys. But remember, in this tutorial, we only focus on one feature for simplicity. So essentially, at the beginning, we process these features based on the nature of the base model. In the case of Deepr, it kind of collapses the visit layer of the input, so that if you have like several visits, it can concatenate all of them together and fill the gap with a special token called gap. So that's what I'm doing here. But bottom line is, at this step, we still get all these string code. So that's what these feature vals looks like. And then we're gonna pass such code-based input through our feature transform layers that you can access them in this feature tokenizer fetching code 2D. So what this step does is it's going to look up all the code corresponding integer encodings. As you can see, the code A05B is transformed to the number 4, A05C is transformed to the number 5, etc. He also does the padding, which is very handy. For example, if you look at the second sample, which only has 3 codes, the remaining entries are filled with 0. That's the padding that's done in this batch in code 2D. I turned on the padding function, the flag. Next, we need a mask. This is kind of specific to the Deepr model, although I believe a lot of other LLM-based models will also need this mask. But essentially, it just tells the model which entries are actually valid. Again, take the example of the second sample. You only had 3 codes coming in. So in the mask, you can see that it has 3 ones and the remaining entries are 0. The next step is that we're gonna transform all these integer code, which doesn't really mean anything to a machine learning model, into dense embeddings. So these self-embeddings layers were initialized in the init function earlier. Now, if you pass X through such layers, you will get, essentially for each code, you map it to a 128-dimensional vector. That's what that step is doing. So as you can see, the dimension now changed to 2 by 6 by 128. Finally, this is what we call the base PyTorch Deepr module. So we pass the embeddings here, which are essentially code level embeddings, through a Deepr model. And it aggregates those codes and adds some transformation so that we now have one embedding for this feature per sample. So again, we are looking at the batch of size 2. It has, the shape is 2 by 32, which just means that for this code feature, we have an embedding of size 32. Now, because we only have one feature in this particular case for simplicity, the next step, patient level embedding, doesn't look as interesting because it's literally the same as the feature embedding that we see earlier. But if you have more than one features, this step essentially concatenates all the different features embedding together into one embedding for each sample. They could possibly be the same patient, but at different time, for example. But anyhow, at this step, we are almost at the end. We already have something that summarizes the batch of data we got. We transform them into logits like usual. In this case, we have a binary classification task. So the logits are just a scalar for each sample. And then you compute the loss by comparing the predict probability with the actual labels and return a dictionary. And that's it for the forward operation. So one thing I do want to emphasize here is all the input to the model is in this quarks through arguments. So this is just for us to make it flexible so that you can, like whatever model you plug in there, the code should be able to run. It just depends on the model whether you want to access those information or not based on the feature keys. What do I mean by that? So, it might be easier if we just look at how we use this model we just defined. So we saw before that a batch of data looks like this, right? It's a dictionary keyed by patient ID, visit ID, and all the features, which are also in batches. So in this particular case, we're passing only list codes as the feature keys. As you can see, when we call the model, we directly use the entire dictionary as the quarks, but the model will just only access listed code features. It will ignore the other ones. It won't report an error or whatever. So it just depends on the model to use whatever information it needs. And here, we initialize the model, we pass the batch of data through the model, and we can see that the model now returns a dictionary of the loss, the predicted probability, and also the label, Y true. So if you are able to, if your model can work on a batch of data, you can now test your model by simply swapping in what we just defined into one of the example scripts we'll provide in PyHealth package. So in this particular case, I think the font might be a bit small for some of you, but I'm using the script called mortality mimic3 RNN. So what I did is literally just replacing that RNN with my PyHealth Deepr, and then you can test your performance by running the script. That's actually pretty much the end of it. But if your model does work, you should consider contributing because it's such a small step between having a working model and creating a pull request and merge a new model into a PyHealth model zoo, I guess. The other thing I do want to mention is that in this tutorial, in fact, in our current PyHealth pipeline, I think we only have EHR data, like the code in time series, that kind of data, just like MIMI data sets. We do want to support, and we're actually working on supporting other modalities as well. For example, images, waveforms. So although your model might have a capability right now and the pipeline might not support those modalities yet, we do think these support will be added in future release very soon. Yeah, that's the end of today's PyHealth Live, and thank you for your attention. Next week, we'll be talking about how to incorporate custom healthcare tasks into PyHealth pipeline. And like I mentioned earlier, you can check out the tutorial I have on the PyHealth website, and you can just play around with that and maybe even just define your own model there to see if it works. And if it works, you can plug that into the existing pipeline and try and test the performance. Thank you again for the attention.